of the power logic. So the contest season for 2024 has already been ended, but there were some really interesting problems from the Aime Ii. So I think this problem is pretty neat, even though I think it's a bit misplaced as the number 13 on the Aime Ii contest. So let's take a look. Let omega not equal to 1 be a 13th root of unity. Find the remainder when the product all the way from k equals to 0 to 12 of the quantity 2 minus 2 omega to the kth power plus omega to the 2 kth power is divided by 1000. So essentially, this is called the capital size of pi, which, well, instead of relating with circles, this actually represents the product, or kind of being similar to summation symbol. Well, it's kind of just like taking the product. So how are we going to proceed? We can let pk equals to omega k. So just to make things like more clear or easier to visualize, then this is equivalent to the product from k equals to 0 to 12 of 2 minus 2x to the k plus x to the k squared. And what does that represent? Well, we can kind of factor the inside thing, right? We can factor this to be what? To be, well, we can kind of try to find its roots, or we can complete the square to see whether we can factor this a little bit. So we see x to the k squared minus 2x to the k plus 2. And we can see that, well, we have a quadratic, y squared minus 2y plus 2. That's equal to y minus 1 squared plus 1. And if that's equal to 0, well, now we can kind of think about using the property that a squared minus b squared is equal to a plus b times a minus b. Well, we also know that a squared plus b squared is equal to a minus bi times a plus bi, since we can factor this into into the product of two complex numbers. Notice that this is basically that a complex number times its conjugate is equal to the square of its modulus. So basically the same thing. So now, y squared minus 2y. Y squared minus 2y plus 2 is equal to y minus 1 squared plus 1, which is equal to what? Y minus 1 squared plus 1 squared, which is equal to y minus 1 minus I times y minus 1 plus I, which is equal to what? Which is equal to 1 plus I minus 1 times 1 minus I minus 1. And you might be asking, well, why is this even significant, and why do we even need to care about this, or why do we factor this into this term, which seems to be more nasty than the original one? Oh, now let's think about that. One of the ways we can say is we can, let's say we just only care about all of the terms in the product which are concerned with 1 plus I. Then we can rewrite it as 1 plus I minus x1 times 1 plus I minus x2, and all the way to what? To 1 plus I minus x sub 12, right? Well, actually, I forgot the first term, which is 1 plus I minus x naught. So now, from here, we can rewrite it as this, but notice that, well, x naught, x sub 1, x sub 2, and all the way to x sub 12 are the 13 roots of a polynomial, which is x to the 13 minus 1. Just notice that 13th roots of unity basically just implies that it's the root of x to the 13 minus 1. So essentially, this we can rewrite it as p of 1 plus I. If p of x is defined as x to the 13th minus 1, right? Now this just simplifies it by a lot. Therefore, all we want to find is one plus I to the 13th minus 1 times 1 minus I to the 13th minus 1. So now the problem has become to evaluate this, and well, you might be saying that, well, this one doesn't seem to be like an integer, but we want the integer answer. So how are we gonna do this? Well, now we can kind of rewrite this as, well, we kind of expand this like a binomial, which we get 1 plus I times 1 plus I to the 13th times 1 minus I to the 13th. Then we minus 1 plus I to the 13th. I guess I need to make a larger parentheses. So basically now this kind of just extract to this. So basically we have these two terms multiplied together, and then we minus both of these, and then we plus the 1 at the end. Notice that this one can be simplified as 1 plus I times 1 minus I, the entire thing to the 13th power, which is simply 1 squared plus 1 squared to the 13th power, which is 2 to the 13th power, right? And now the only nasty term is this thing. Well, we can see that this one is actually really symmetrical. But if we want to expand this, it's gonna be pretty annoying. So essentially, now here's a trick. So notice that the value 1 plus I over root 2 is actually the 4th root of unity, which implies that it's basically e to the I pi over 4th power. So essentially, we can divide this entire thing by root 2 to the 13th power, and then multiply by root 2 to the 13th power. So essentially, we would have So notice that 1 plus I root 2 is basically equivalent to a point on a unit circle such that it lies in the first quadrant, and its angle with the horizontal is actually 45 degrees, which is e to the I power 4th power, right? Now let's think about what is the other one. Now the other one, 1 minus I root 2, is basically, think about it, it's a reflection, reflection of the 1 plus I root 2, across the x-axis, which basically implies that it's basically its angle corresponds to 7 pi over 4. and then don't forget a +1 at the end. Now here, how are we going to evaluate this? Well, we can evaluate e to the I power 4 plus e to the 7 I power 4. And notice that because they're actually like reflections across the x-axis, then when we add them together, then their y term, or like if you draw it in the complex plane, then their imaginary number would cancel out. So that is why we are confident that we're going to have an integer or at least a real number answer. So this problem is actually pretty nice because it's like really symmetrical. Now we just want to evaluate, well, basically 2 times the real term or the real part of both of these, which are both what? Root 2 over 2, which is 2 to the 13 plus square root of 2 to the 13 times square root of 2, right? Since we know that both of these complex numbers have a real part of square root of 2 over 2, and 2 times of that would be square root of 2. Now, this basically was equal to 2 to the 13 plus what? Plus 2 to the 7 plus 1. Now 2 to the 13, we know that 2 to the 12 like is 4096, so 2 times of that would be 8192. Like you can just try to like verify this on the scratch paper, and this would not take so long. So this one is basically 8192 plus 128 plus 1, which is equal to 8322, and that is our final answer. Thank you for watching, and I hope you enjoyed, and I hope to catch you in the next video. Peace out.